We've already spent time with exponential growth, so let's go to exponential decay. Let's look at the medication cefaclor, which is used to treat ear infections and sore throats. The recommended dosage is 40 milligrams per kilogram per day, with the divided dosage being given every 8 hours. So let's go back to our dosage problems. What is the recommended dosage for a child weighing 50 pounds? Well, if you weigh, as a child, 50 pounds, we're going to use the given approximation that 2.2 pounds is 1 kilogram. So that gets me out of pounds into kilograms. And then we know the dosage is 40 milligrams per kilogram. So that gets me into milligrams. Now that's going to give me an answer of approximately 909. But it says you're given it every 8 hours. That means 3 doses. Divide this by 3, and you have 303 milligrams of cefaclor in each dose. Now the half-life of a drug is how long it takes for the body to cleanse itself of half the drug. So what does it mean if we say this drug degrades by 50% each hour in the body? And then how much of the drug remains? Well, if in this example, if we have 303 milligrams, if we say it degrades by 50%, 100% is all of the drugs. If it degrades by 50%, that means 50% remains. That's what it means. In this case, we multiply by 0.5, and 151.5 milligrams is left after the first hour, because it says each hour. So we're going to do our table. After the first hour, we're at 151.5 milligrams. And then you would take that and you would multiply that by 0.5, 50%, and you get 75.75. Multiply that by 0.5, and you're at 37.875, and so on and so forth. You're going to finish the table in a minute. But I want to go to the absolute and relative change columns. Remember, absolute change is new minus old. Relative change is new minus old divided by old. So let's just go from 1, where this is new, this is old. So we have new minus old gives me negative 151.5. So my absolute change is negative 151.5. Makes sense that it's negative, right, because we are decreasing. And then we divide by the old to get it relative, and we get negative 0.5 or negative 50%. Right? Okay, so using that, and we've done this now for multiple sections, go ahead, hit pause, finish the table, and come back and check your answers. All right, I rounded because it's really hard to write in those small spots with your finger. So when you're doing your calculations, you want to take them out to as many decimal places as humanly possible in order to keep your answers as accurate as possible. But you'll notice that your absolute change for each of these is actually just the negative of how much is less in your system, and that makes sense. You cut it in half. And because we cut it in half, when you look at your relative change, for all of them was a negative 0.5 or a negative 50%. For all of them, and that makes sense because, right, it's going down. So, which is the same from hour to hour? Relative change. What does the negative relative change mean? Well, it's a decrease. So just like a negative absolute change showed a decrease, a negative relative change also shows a decrease. What is the percent decrease? And we found that to be a 50% decrease, and that's the last column. Right? The word decrease implies a negative sign, so you don't need to have both of those. Number 7. In exponential decay models, there is a decay factor, 1 minus a percent decrease. What is the decay factor for this model? Now, the percent decrease we know was 50%, so as a decimal it's 0.5. So if we take 1 minus 0.5, our decay factor is 0.5. Which we kind of already talked about in that we multiplied each time by 0.5 to find the next answer. But you'll remember from exponential growth that our growth factor was 1+% decrease, or 1+% increase, so it makes sense that if we're decreasing, we're subtracting. And you'll notice that our formula is the same. Amount equals the initial amount times the decay factor raised to the time period. That's a T. The decay factor just like your growth factor, except we're subtracting. And new divided by old still gives you your decay factor. So if we want to use two consecutive factors, I'm just going to use the first two. So when it was initially we were at 303. After the first hour, we're at 151.5. So that would make this new and this old. So 155.5 over 303 gives me 0.5, and there's my decay factor. You'll notice that decay factors are less than 1, and growth factors are greater than 1, because you're multiplying. Okay, so this is a graphic of the cefaclor remaining in your system. What would be represented on the x-axis down here? And that would be hours since administration of the drug. I should have used a different word besides administration, but hours since the drug got shoved into your system. On the vertical axis would be milligrams remaining. And what should you put as a title? You could use those as the titles. Hours since administration could be on the horizontal axis. Milligrams remaining could be on the vertical axis or the y-axis. Now, what's the model for determining the amount of cefaclor left in the system after T hours for this child? Well, you start with y equals initial amount, which is 303. We found our decay factor to be 0.5, and it says T hours, so that would be T. All right. Now, let's change things up. What if it degrades by 60%? So that means we would have 1 minus 0.6. My decay factor would be 0.4. Okay? So, if we're thinking about this table, instead of multiplying by 0.5, because my decay factor was 0.5, now to find after the first dose, we would take 303 times 0.4, because now we're at 0.4. That orange doesn't show up very well. And I'd be at 121.2. For the next one, I would take 121.2 and I'd multiply by 0.4, and I would get 48.48, right? It's degrading faster. There's less in your system. Multiply by 0.4 again, and we'd be at 19.4. I'm going to start abbreviating. You can go ahead and hit pause and finish this if you'd like, but I am going to round because it's hard to kind of write in there 1.2, 0.5, 0.2, 0.1. And I did round there pretty significantly. But you can see that the drug goes away quicker if you have a 60% degrade compared to a 50% degrade. What would that model be? Well, we're still starting with our initial amount of 303, but now my decay factor is 0.4. So because it's degrading at 60%, the decay factor is how much is left. If 60% is going away, 40% is there, and that's why I get the 0.4. When would the child need another dose? Well, okay, so I'm going to give you whiplash, and I want to go back to the original table. This one said they needed a new dose after 8 hours. So it's my assumption that when the milligrams become less than 1, that's when you need a new dose. I don't know if that's true. I'm making this assumption based on the data that's in front of me. So when I look at this shows me that I drop under 1 after 6 hours. So when do we need a new dose? After 6 hours. And I'm not sure if that's true or not, but I'm using the data you have, and that's what using data is all about. Use the data in front of you. So this kid needs a dose after 6 hours because it leaves the system quicker than the other one.